Hello friends, welcome to engineering tutorial. So in today's video we are going to discuss about another arithmetic combinational logic circuits, which is full subtractor. So we have covered half adder, we have covered half subtractor, then full adder. Now it's the turn of full subtractor. So just before that, a quick review of the digital logic circuits. So this full subtractor, it comes under the category of combinational logic circuit. Okay, arithmetic combinational logic circuit. Combinational logic circuit which is used to perform arithmetic operations. So there are two categories, combinational and sequential logic circuits. In combinational logic circuits, the output at any instant, it depends only on the present inputs, the value of the inputs at that particular instant. Whereas in sequential logic circuits, it depends on the present as well as the past. That's why there is a memory element present in sequential circuits, which is absent in combinational logic circuits. So the basic block diagram of a combinational logic circuit is the block. It is formed of different combinations of logic gates, basic logic gates such as NOT, AND, OR, XOR, XNOR, the universal gates NAND, NOR, which are arranged in different ways according to the logic implementation. The Boolean algebra, which we have to, the expression which is in Boolean algebra form, which we have to implement. So it consists of n inputs and m outputs depending upon the requirement. So we have covered, like I said, we have covered half adder, half subtractor, full adder. Now we have to will see the full subtractor. This constitutes the arithmetic circuits. Then there are other circuits as well, such as encoder and decoder, multiplexer, demultiplexer, then comparator, parity generator checker, code converter, which we'll discuss in the upcoming videos. Now, the arithmetic circuits, like I said, they're used to perform basic arithmetic operation, addition, subtraction, and for multiplication and division, multiplication which is repeated addition and division which is repeated subtraction, they are done by manipulating the adder and subtractor circuits. So in full subtractor, what is the difference between a full and half subtractor? So in half subtractor, it involves the subtraction of only 2 bits. When there are only 2 bits involved at the input side, there are only 2 bits involved, like this. 0 minus 0, 1 minus 0, 1 minus 1. So whenever there is a borrow involved, like this, the fourth case, where there is a borrow, which we have, where we have to borrow something for subtraction, in that case we have a borrow input, and for there are 3 bits involved, the 2 bits to be subtracted and the input at the borrow side. So here for full subtractor, it is used for the subtraction operation of the 2 bits which are involved, and also it also takes into consideration whether there is a 1 which has been borrowed from the previous adjacent bit or not. Okay, so there are 3 bits to be handled. So in full subtractor, there are a total of 3 bits at the input side. The 2 bits to be subtracted, okay, here. So here for full subtractor, there are 3 bits which are involved, like I said. The 2 bits that are subtracted, okay, minuend and subtrahend, and this third bit, which is the borrow from the adjacent bit, which is taken at the input side. Okay, and we have 2 outputs here. First is the different and the borrow which is generated at the output side. Okay, so this is full subtractor. What is its difference from the half subtractor? In half subtractor there was only 2 bits, A and B, no provision for input borrow. Okay, but there was provision for output borrow, difference and borrow output, but the input borrow was not taken into consideration, okay, for full subtractor. So this is the basic block diagram. Like I said, every combinational circuit we can express it in the form of a block diagram. So this is the block diagram. It has 3 inputs and 2 outputs, because as per the requirement of the full subtractor we need 3 inputs, the 2 bits to be subtracted and the input borrow, and 2 outputs, difference and output borrow. Okay, so the logical outputs of these 2 outputs, that is difference and borrow, they are expressed as this. So we have the 3 inputs A, B, the 2 bits to be subtracted, and the input borrow B in. So the 2 outputs are D and B out, difference and output borrow. So the logical output of the full subtractor, it is the difference output D is given by A XOR B XOR B in, similar to full adder. So it is expressed as this: A bar B bar B in, or A bar B B in bar, or A B bar B in bar, or A B B in. So this is AND here. So this, when I say A bar B bar B in, it means A bar and B bar and B in. This is AND. This is OR operation. This is AND operation. Okay, always remember that. Okay, similarly, the borrow output is given by A bar B bar B in, or A bar B B in bar. So when I say A bar B bar B in, it is A bar and B bar and B in. Similarly, this is A bar B B in bar, A bar and B in bar. This is A bar and B in, or A and B and B. And the simplified form is expressed as this. Okay, the simplified borrow output, which is A bar B or A XOR B bar into B in, which is A bar B or A bar B in or B in. This is the simplified form, which we'll see how it comes to this. Or in other way, we can write it as B output is equal to A bar B or A XNOR B into B, because inversion or NOT of XOR gives us XNOR. Okay, XOR bar gives XNOR. This is XNOR symbol. Okay, so this is the simplified borrow output. This is the lengthy one. This is the simplified one. So we'll simplify it using K-map to get us here, and how we will get this from this we'll see. Okay, I will tell you. Okay, so the main requirements for a half subtractor. Now again, half subtractor can be designed in various ways. We can design it, this Boolean expression, these 2 Boolean expressions, okay, we can implement it in different ways, like we have seen in the previous arithmetic circuits. We can do it using basic logic gates involving XOR or without XOR, or we can do it using only universal gates, that is NAND gate, only NOR gate, or we can implement it using multiple half subtractors. So all those cases we will see in separate videos. Here this is the most general form, okay, the most general logic diagram of full subtractor. So here the difference is A XOR B in. So what we do, we have divided this into 2 stages. So in the first stage we have XOR gate. There are two inputs A and B. So we get the output A XOR B. Then we take A, pass it through a NOT gate to get A bar here. This is A bar here. Then A bar and B, we pass it through a AND gate to get A bar B. So we have got, this is the first part. Then again this A XOR B, we pass it as one input to another XOR gate, and then the input borrow is provided as the second input to that gate. So we get the difference output A XOR B XOR Bn. Then again this A XOR B, this is A XOR B. We pass it through a NOT gate to get A XOR B bar. So again Bn, we provide it as the second input, A XOR B bar as the first input. Through another AND gate, we have A XOR B bar into Bn. Finally, A bar B and this output A XOR B bar into Bn, we pass it through a OR gate to get A bar B or A XOR B bar into Bn. Okay, this, because A XOR B bar is A XOR B into B, this. So we have XOR gate, AND gate, two XOR gates, two AND gates, and this final OR gate we have used to implement this Boolean expression. For difference, A XOR B XOR Bn. For borrow, we have used this expression, A bar B or A XOR B bar into Bn. This is the most general form using minimum number of gates. Now we will see how we will do it through basic logic gates involving XOR and XNOR and without XOR XNOR, then using only NAND gates, only NOR gates, then using two half subtractors. Then we have the truth table. So this is the truth table of full subtractor for various combination of the inputs A, B, Bn. We have the difference and borrow output, you can see, and you can check. You can put these values in the the Boolean expression and check whether they match. So this is the truth table. Okay, so here we have discussed in a general way the basic concepts, the design and working principle of full subtractor. Okay, so in the upcoming videos we'll see the K-map implementation, then we'll discuss the various implementation using different combination of logic gates and so on. Okay, so now we will see how the borrow output. Okay, we know for full subtractor we just saw that the borrow output can be expressed in different forms. So one of the ways of expressing the output borrow is A bar B or A XOR B bar into and Bn. Okay, by mistake I say into, it is AND. Product means AND in Boolean language, the Boolean. Now also borrow output can be expressed as, in the simplified form, is A bar B or A bar Bn or B Bn. Now we'll see how this is equal to this. So in another way we can also write this as A bar B or A XNOR B into Bn. This is XOR, inversion of XOR gives us XNOR. So this. So we'll see how this equals to this. Okay. So first let us take the borrow output A bar B or this A XNOR, directly we'll write A XNOR B into, and B in, sorry again. Okay, now we know that A XNOR B here is AB or A bar B bar. A XOR B is A bar B or AB bar. And we have discussed in Boolean algebra laws. Okay, you can please watch the digital electronics playlist where I've discussed everything in detail. Okay, you will find all the videos there. So we'll put in place of A XNOR B, we'll put this expression. So we'll have A bar B or AB or A bar B bar B in. So now when we open the bracket, we have A bar B or AB B in or A bar B bar B in. Okay, this. Now here we have B common in these two expressions, B here, B here. So if we take B common here, B A bar or A B in or A bar B bar B in. So here X or X bar Y is equal to X or Y. Okay, this. So here it is A bar or A double complement. See, A bar or A B in is same as A bar or A double complement B in, because a double complement of a variable is essentially the same thing. Okay, so here it will be B in and A bar or B in. Or A bar B bar B in. Okay, now again if we open the bracket, we have A bar B or B B in or A bar B bar B in. Okay, now if you see in these two expressions, in terms, we have B in common. So again we will have A bar B, or taking B in common, we have B or A bar B bar. So again this X or X bar Y. So B or B bar A bar. So it will be A bar B. Again using the same concept, it will be the same Boolean algebra law. It will be B or A bar. Okay, so this. Now if we open the bracket again, it will be A bar B or B B in or A bar B in. Again rearranging it, A bar B or A bar B in or B B. This is the same as the Borrow output which we discussed in the first thing, the different ways of expressing the Borrow output. See this, A bar B or A bar B in or B B in. Same here, A bar B or A bar B in or B B in. So this is through Boolean simplification of the Boolean expressions, we got the same result. Okay. So the other minimization, we'll do it through K-map. Okay, we'll see it there.